these are the three keywords for today: correlation, significance, and it seems like we've done some of that already, but we're going to make more sense of it. And now I'm going to add cross correlation in front of it. And I'm also going to add the words lag and delay to it. And let me begin by sketching a situation that I would like your opinion of that ties together some things that we've already done. So here's a data set. X and Y. And let me ask you, what is the general behavior that I expect in this space if, let's say, X is the temperature in Boston, let's say, and Y is the temperature in a southern city, an equivalent amount of degrees south of the equator than Boston is north of the equator. What's the sort of general behavior that I expect? And I'm going to go down the list in numbers, and I begin with fog. Still want to hear all your little voices again.
The general behavior if they're just different laterally?
So same latitude north as south, two cities. And what's the behavior of the temperature? Like I want to sketch something. I want to just plot some dots.
Oh, going north should make it colder. And
I mean, I want to sketch the behavior through time. I did not say this. Okay, let me begin by this here. Remember that we're talking about time series at some point, and that we talked about interpolation, and one of the reasons was to eliminate a third variable, which in this case is time. So now let's say X here is my temperature in, I don't know, let's say 40 north as a function of time. And my Y is another variable, but of the same type, the temperature, but it's now 40 south as a function of time. And you know what a temperature time series through the year look like, ups and downs and so on, in this city and versus that city. And now I want you to mentally eliminate time and just say, well, for a certain temperature in Boston at the same time, I will plot the temperature in this other city. So this point here, the little x star, and the little y star, that's a point on my graph. Well, so it's positive, negative, so that's here, okay? And so now I want you to eliminate the time variable and tell me what sort of graph I will sketch if I do this for every temperature at every time, but thereby eliminating the time variable. Is the question clear?
I think so, and I think it would start looking like a line because as one goes up, the other would go down.
Yeah, but then the other one goes down and goes up again.
Oh, so it would just make the one like combined wave.
So how do you combine that?
Oh dear.
I'm going to go in I'm going to ignore all the raised arms and I'm going to go in the list, the master list. Which you can't see. Here's the master list. Shall I call the next fog turns to snowstorm?
Like if one goes like down as the other goes up, then it would be a negative like correlation. So like it would be aligned with like a negative slope, like in your y versus x plot.
Okay. Snowstorm turns to drizzle.
Wouldn't it be a circle? Am I silly in saying that? It'd be like, because if they're out of phase completely, it's, and is that wrong? It's probably wrong now that I'm thinking about it.
So be affirmative and let's think it through. And if you're wrong, then what's the big deal?
Okay.
Right? So here's what I hear you say, drizzle. You're saying, well, wait a minute. We also, in another lecture, we're talking about, X as a time series. And think about temperature in Boston. Is some sinusoidal components of something where, remember, we are saying 2 pi over a particular period, which I now call red p here, times little t for time, plus some arbitrary phase, not arbitrary, but something I don't care to specify now, something that exists, times some amplitude, which, I don't know, I'll just call big T of little p, okay? And previously we were saying there will be other components. There's a 24-hour cycle, there's 183 days, there's a 200, there's 365. You guys have figured this out for your own temperature. And now I'm saying y of t, by saying it's the same degrees north as south, I mean to imply that it's likely to be close in the amplitude of the cycle. And the general form is respected because it's still the Earth rotating around. So here is 2 pi over the period. Actually, it's little t over the period, which I should write, but that's sort of how I wrote it. Okay, so it's however many times your time variable fits into the period. If it fits 0 times in it, you're at 0. If you fit once in it, you're at 2 pi. If you fit 2 times in it, you're at 2 times 2 pi, and so on. Plus some phase. But the northern phase is going to be different than the southern phase. And what I hear drizzle saying, fog, is, well, the phase angle here, this difference is going to be, and you called it completely out of phase. What does that imply for a sign to be completely out of phase?
That when they subtract, they get, that they're, when they subtract, they get 90 degrees, right?
So 90 degrees is how many radians?
Pi over 4. Or
Is
pi
it?
over, no, pi over 2. I'm so sorry.
Okay. And so if you have a phase difference of pi over 2, and let's say phi n is 0, and then the pi over 2 is a cosine, then you have indeed a trajectory, and now I'll say plus noise, plus some, whatever fluctuations that I'm not modeling here, a little epsilon, the unmodeled components. Well, this from 3rd grade, if you plot the trajectory of a sine versus a cosine, that you get a little circle. Okay? So My ideal circle is a geometrical figure. The noise is, I'm not perfect in my data, and plus there's other things going on. The size of my circle is the size of, the amplitude for that period. I start here through the year, I'll make that a solid dot. I'll give 3 references here. I'll make a red dot for something that is, later, when X has gone negative. And here's that plot point. And so mentally you go through and maybe mark another point, I don't know, a solid triangle. Whoops. And that is, what is X is positive again, and the Y is 0. So I'm not drawing it perfectly well, but just to make sure it's not terribly wrong, I would be about here, right? A little negative X, oops, here, and a little negative Y, so I'm sort of here. All right. Okay, so just drawing some dots and so on. So you know now that these signals, temperature north, temperature south, saying equivalent cities, they're very much alike. They are completely related by the rotation of the Earth and the axis and the inclination of its axis. They are, in other words, massively dependent and correlated. But you also know that if I plot the correlation coefficient as defined by, first of all, let me write it, the correlation coefficient as defined multiple lectures ago. And I'll reach for my notes here. Remember this, where we had a point cloud and we shifted it to a mean value and we scaled it to a variance. And that's what many of you do in your projects also, right? This is the normalization, mean shift and scaling, spread scaling that tends to normalize. And if it begins to be normally distributed, then it tends to be standard normally distributed. So that's always good practice. If I define this to be the sample correlation coefficient, and I was a T here for temperature, except I was here for relative humidity, right? We subtract the mean value. I've kind of already done that by calling this point 0, 0. Scaled by the spreads. In this case, that doesn't matter because it's the same functional form, so the spread is the same. And the measure of that spread is the size of the circle. And then divide by it. Done, that's done. Okay, so what is the correlation coefficient for this data cloud, rains frogs?
0?
Exactly, right? So this is a good step on the way to realizing why, first of all, having a 0 linear correlation coefficient doesn't mean the data have nothing to do with each other. It just means they're not linearly correlated. And so, that's exhibit A, okay? So now what would happen if I moved my Boston, to way up in the north, higher and higher latitude? Your seasonal cycle will change. What happens in particular if I make the y-axis twice as large of a circle, sorry, of an amplitude, then I'm going to stretch this circle in an ellipse that's oriented along the y-axis. If I made the x cycle twice as large, I'm going to squeeze that into an oblate ellipse. If I now fiddle with the rest of these variables, then I can get any shape of an ellipse. And so let's go to that situation where you have some variable of interest now for you guys, some random x, some random y, and you are seeing one of these, you know, when I'll sketch the contours here, sort of an elliptical type of relation, where again, it's implied that you're on some temporal trajectory. I'll do some solid dots to indicate that at least you keep track of the progression of time. And, you know, that's how these samples turn out. Again, a collapsed time series in two variables where you've eliminated the time itself. Okay. What is the correlation coefficient of this point cloud? And that is the question for Anvil Cloud.
It appears to be greater than 0, but still small.
Okay, so let's say positive. Right? Because you want to see this axis. Okay, so ellipsoidal trajectories tell you these data are related. So I do want to add the word trajectory here because it's not just dots on a graph. That's what we used to have. Now there is a notion that there is a progression here. Clearly, it is just dots on the graph, but there is a non-shown dimension here, which is that time. If I drew this, it would be a little spiral, right? Time would go going up like a screw. Anyway, so if you now know that you have some generic relation like this, and you got some indication of a correlation, but remember, don't stare blindly at the correlation coefficient, because in this case where the data are perfectly well related, the correlation is still expected to be exactly 0. So you gotta look at your data, you gotta see the time progression. So now I'm sketching this situation. And here is my X again. And here is my Y again. And there's a time again. And so I'm gonna not, you know, draw it perfectly well here because I'm just gonna sketch it. So I want to see some sort of a underlying oscillatory behavior in time. And for my Y variable, I want to see that also. And I don't want to, you know, if this is a cosine, I don't want it to start as a sine, but I want it to start at, you know, a little bit later in the phase. So I'm just going to sort of sketch it like this. Same period, but a phase difference that isn't exactly 90. That's this. Remember notation, the distance between two crests, in this case is a period, that's P. That's unchanged here, but my crests occur later. All right, that's unchanged. If you want to think about this initial thing here as indicative of the phase, you can. Phase as what is the value on the inside of your sine, of your cosine, And if you subtract this thing, then it's whatever that difference is from where you're at. So it's a little phi. That gives you where you're starting. And plotting the trajectory shows you what the relation is. So now let's try to measure what the, the point here is that if you're doing this cross correlation, this correlation, where you're not changing time, you're just going to get these trajectories and you're going to get correlation coefficients that will give you a measure of a linear correlation, but it's not going to be very good because it doesn't back out the full trajectory. So if you played the mental game where you pulled one of the data backwards on the time axis, and let me literally pull this y-axis down back by some value t, tau rather, that's my tau, but I'll say t now and then, Greek t. Then that's the same as me saying, okay, I'll have a new time axis, which now starts at 0 here. T minus tau. So I'm not doing anything except re-baselining my time axis. If I really did this properly, I'd take a scissor now and I'd cut this out and I'd move it and stick it on the left a little bit. In order to do that, I will now just draw tie lines between equal points in time. So here is time 0, and here is time some other time, and so on. So I've just shifted it all, which means I get these tie lines. So what would happen if I made a cross plot of y and x after shifting one of the time axes by tau? And that question is for tropical storm. Let's say I've done this. I've moved my y-axis down by the appropriate amount such that, like in my sketch, at my time 0, I'm actually at the top of the crest here, just like I was in my X series.
So it's like you've shifted it back so that they're both in phase, like the same phase, essentially? Yes. Okay. Yes. In that case, I know that the correlation coefficient would then be probably strongest there. Yes. Graphically, would you have a line, I think? Like just a linear correlation between the two?
Okay, that is exactly what happens, right? So you imagine that it's the same sign at the same phase, except there's some noise terms in there, which means that you have the canonical example of, least squares line analysis, where, you're up and above some line. And if you do a cross correlation coefficient, weakly positive, and you do it here, I'll do it like, whoa. That's when you get a strong, big positive, right? Near 1, I'll say. Okay. So this variable here, the amount by which you need to shift it in order to maximize your correlation coefficient is an example of a lag, lag as in delay or time lag. And so if I right now and right here, I define tau, as the lag that maximizes the correlation coefficient between x of the original t and y of my newly lagged t, then I have at least a working definition of how similar these time series are when trying to align them over all possible lags, and then figuring out what the best one is and calling that's the one that squeezes this ellipse mostly into a phase relationship. Okay, so starting from a circle, same amplitude, you'll lag it by an equivalent of 90 degrees, equivalent by how much time you need to add, or in degrees, it's already in degrees, and you make that a line. And same with the ellipse and so on. And so those of you who've ever played with an oscilloscope, which I realize is a vanishingly small number of you, probably, but you gotta imagine an electrical apparatus that takes two wires with current coming in. Do not do this at home, but you stick one into your wall outlet, lightning storm, typically. What is the frequency of that, of what comes out of your wall outlet?
Like the actual like frequency of mine, I have no idea, but like.
And don't do this at home.
No, I do not do this at home.
Idea of what frequencies come out of your wall outlet? No. Okay. It's not like 60 hertz or something. So, two wires describing two oscillations, not exactly in phase. You feed them into this electronic thing that plots on a little axis what comes in, doing exactly what I'm doing, eliminating time, then turning a knob, delaying one versus the other, and then when they're exactly in phase, you hit the line, and then you measure the correlation coefficient. That's more or less what one of these instruments does. That's called an oscilloscope, which is where you might learn it in later classes also. They still use that in engineering labs. Okay, so this you could do. Hopefully, tell me if you have any questions. I'm trying to make this conceptual so you can see what's happening. And now you just have to believe, right, that there's already a MATLAB thing for it, and that the function that trying all combinations of lags, both positive and negative, and at every point calculates a correlation coefficient, that function is called X-core. And that's because that operation is called cross correlation. Really, the cross in correlation refers to the fact that you are not looking at the same signal. So there's an X versus Y. That's the meaning of the real cross. If you do it with yourself, then it's going to be called autocorrelation. But the word correlation here, in the way this is defined, implies that time progression, that trajectory, that whole thing that I've been describing. And if you use that word for the thing that actually implies time trajectory, then the good old cross correlation that you have been using, which was called core-coef, the function. Correct me if I'm wrong, I think it's 1f, right? Core-coef, I guess. That's a MATLAB function, .m. Then technically, that's going to be called a zero lag cross correlation. But those are just words. And so, if you go back to the definition of the correlation coefficient, the coefficient comes in, this is what's called Pearson's correlation coefficient. And that's the thing exactly as written here, which has shifted and normalized over the scales. If you just invoke cross correlation, it literally just multiplies x times y after lagging. But you can give it options that say, well, by the way, just give me the coefficient version or normalize it this way or that way. In other words, you can scale it whichever way you like. In the Pearson correlation coefficient, the normalization or scaling is by the variance of the signal square root, so the standard deviation, and the shift is with respect to the mean. So if you use cross correlation out of the box, you might as well feed it demeaned and scaled data, certainly appropriate. Or you could ask its internal implementation to do it for you, but so read the options, it does multiple things. The important thing that comes out is that it will give you a value for all possible lags, shifting x compared to y, or rather shifting the time at which x is coded compared to the time at which y is coded by the amount tau. And then it'll say, like in my example that I'm trying to pull together here, well, look, I had to switch the y series by an amount tau. So I have to delay it by tau, and I'm going to get the sign wrong, but if it's not on the right, it's on the left, right? So for a tau of a little bit, that's when I will maximize my correlation coefficient. And if I'm in temperature in the two places and I've already normalized, then I expect this number to be around 1 after I do that. And so in my schematic here, at my tau, I'm going to get a high value. And then if you begin by doing it, you get the initial situation, you get a low value, which is no shift. That's the zero lag cross correlation says, well, these things are not linearly correlated. No, because they're two signs, they're related. They're just not linearly correlated. And everything in between. And depending on the normalization and so on, you're going to get a curve here that I'm just gonna, hand sketch here, wiggle, 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 going big, decaying again, and then whatever else it does. And so that's how you guys, when you're looking at two things that are possibly in different phases of their oscillation, because maybe different latitudes or maybe different responses, maybe delayed response of evapotranspiration to insolation, or, your cloud is overhead, but your soil doesn't heat up until X minutes later. If you suspect a correlation between two things, but just cross-plotting it at the same time just doesn't bring it, but you're seeing a hint, or you have a mechanistic explanation for why there might be such a behavior, then you all really should be doing a cross correlation. And what you get out of there is this red curve. And then you're asking, what is the max of the cross correlation? And once you found the max, you determine the optimal lag. And then if you want to go back and say, now you can redefine the time and shift the signal by the other one, then you can finish with the last run of the correlation coefficient after having adjusted the time. And then of course you're going to get the same value, except now you'll know that you have had the maximum. And then you can move into the question was that whole thing significant enough, which I will address in a second. Because if I haven't said it clearly enough, it's not enough to maximize the cross correlation coefficient and say, this is it. You also have to then report how big it was and whether that was actually big enough for you to conclude that there was that relation, right? So it's not enough to say it's the best you can find. You also have to summarize, is this actually good? And so that brings us back to the postponed question of, well, once we've done that, we may have found the best lag, but we also owe ourselves the explanation of how strong the correlation is and whether that is significant. So questions before I go on, comments, general reflections. Nothing? If there's absolutely nothing, then that almost means that there will never, ever be a question about this.
I mean, it's not really a question, I guess, but I'm just like trying to think how effective is this in explaining? Because if you want to use this as like maybe a predictor or something, then there would probably be other factors closer to the time period if you're like looking at how much you're offsetting like the time by. And on top of that, like we use like sines as our example earlier. And if it really is a sinusoidal curve, you would expect to see multiple maxes, right? So then
that's definitely true. And that is a key point, and that's why I was vague here on the left and the right here, is that very often in analyses like this, there is a complete ambiguity because of, you know, the periodicity of the sines and the cosines. And that can, you know, either inspire you or bother you, or shouldn't inspire nor bother you, because if things are periodic, then there's no surprise that every 2 pi you lock it back into phase. Okay.
Mm-hmm.
So for you guys, if you're thinking, you know, one city versus another or one variable versus a response, you are not going to really worry about the fact that the heat of that, you know, that the temperature of my soil here is going to be responding to 3 years ago midday temperatures, right? Although that is not a stupid question, because as you go deeper down in the earth, there are oscillations being felt from earlier and earlier. That's a sort of separate question, but if you drill a big temperature borehole, then there is an effect there of even ice age fluctuations, because the deeper you go, the soil, the dirt, the earth, the rocks haven't had time to respond to every driver. But if you're digging in your centimeter of soil here and you're saying, what is the temperature of my little soil probe? Well, it's going to go with whatever the temperature is right next to it, above it, whatever the solar driver is. But if there is some kind of a delay, it will be small, right? So in examples that I can think of here for
hold on a sec. I think everyone, virtually everyone in this class should be able to think of an example that this will work exceptionally well for. So think about all the different weather data you're working with. Some of you have already even hinted at the prospect of there being a lag. Can someone speak up and describe where they might expect a lag in relating to variables in their data set?
So like for like the data that I'm looking at between cloud cover and temperature, if like clouds do lead to like increased temperature, that would be like a lag between those two. It's like temperature would go up like after a certain lag of increased cloud cover.
Yeah. I mean, you'll see snowstorm that I'm responding to your email, but I think it's very unlikely it goes in that direction, but likely the opposite. So if you warm the surface, there could be a lag between that time and the time when the air has risen high enough to condense and form clouds. Now that time scale is pretty short. That time scale might be on the time scale of hours. And perhaps you can see some kind of lag like that. How about someone else?
I was actually going to say the same thing, but I think in the last assignment where I did cloud cover, I think I kind of saw a little bit of that, saying that, oh, the cloud cover is coming after the temperature a little bit. And so that might have been like one case, I guess. But I was wondering, like 30 years data, that might be a bit trickier, I guess.
Well, it turns out that the lag, that temperature lag with cloud cover is seen on many scales. So very locally in a single day of deep convection with cumulus clouds, it might be hours. But think about also like a seasonal transition. You know, imagine you're coming out of winter and you're starting to thaw the ground and it's starting to warm, and all this snow that previously wasn't really available for moisture is becoming water. Then you see this lag between first melt and first temperature warming, and then eventually the first clouds and rains of spring. And that lag is on the scale of weeks to a month, as one example. So it turns out there's a huge number of weather phenomena that have pretty poor straight correlations, but pretty amazing lag correlations, because they're all interconnected. Another example would be, for example, wind and pressure, or even potentially temperature. So if you're locally changing the pressure, let's say that the day is moving on, it's warming up, the local pressure is decreasing because the air is rising. Well, eventually that local decrease in pressure is going to cause air from nearby to want to blow towards you, which is going to change the temperature locally. It's going to change the wind speed. And ultimately, if you compare the two variables directly, pressure to these others, their direct correlation might not be that great, but their lagged correlation might be amazing on multiple timescales.
Back to the phase ambiguity. Yes, very often you'll have multiple oscillations and you won't know exactly which ones to tag in. This has not been on the examples here, because when you're talking days or weeks or compared to these yearly cycles, that's not going to happen. But there very well will be cases where you will need to deal with that, and that's just par for the course. Cycle skipping is a name for that. What is the other name for that? Now I'm blanking on it.
The other name for what? Aliasing?
When you're undoing the jump, when you're when you're like you hit pi, 2 pi, and then you go back to zero, or when you, and there is in radar processing, there's a name for that. Unwrapping, that's right. So you unwrap the phase, and then you still have the phase ambiguity. So this happens in geodesy, this happens in radar processing, this happens all the time. Seismology, unwrapping. Anyway, so I want to give you the couple of line examples, which I realized two things, and I will share with you what I just realized. One is the following, that my older version of MATLAB, the example I was going to show you, came up when you typed help xcore. Now I just did it, I emailed it to you. We're going to do that, few line examples so you can see it. I realized two things, that in the latest version of MATLAB, they no longer give the same example, which is just annoying. I also realized that they didn't proofread their own thing, because here they're doing exponential sequences. So one of you, please be my guest and tell them to fix it, and then you might get your money back. Anyway, we're not dealing with exponentials. And let me check my email to see that I got my own email to you, which I sent a minute ago, because that's the example that there used to be. Where is it? Did you get it? Did you get my email, or did I send it to the wrong class again?
We got it.
Okay, I just need to maybe
Got it.
just take a quick look at it. I need to copy it another way because I'm not sure what it is. Just read it. Don't even need to do it. Just read it. Here is it. I will now get it. That. Okay. So load noisy signals hopefully still works and gives you some noisy signals. You are seeing my screen. I will open a figure. It will take forever. There it is. I'm just going to do a quick verification of my sanity here. I'll do a subplot 311. I'll plot S1. A subplot 312. I'll plot S2. I'll wait for what seems like forever. And so, you know, this literally might be you and your laser gun doing, you know, quality police work of checking somebody's speed, or you tracking a satellite in space, or you measuring something underwater with acoustic waves or anything. I don't know what it actually is. Then we're going to get the correlations and the lags. And here I'm not normalizing anything. I'm just calling it out of the box, which assumes clearly that you can do it because both the signals are zero mean and on the same scale and represent the same physical quality. Fine. You're finding the max of the absolute. The time difference between these things, I'm going to eyeball it. Here, you guys eyeball it. Fog, what is the time difference between the signals in units as plotted?
About 100 years. No. Seconds?
Well, whatever the unit, I don't know what the unit is, but are we talking about this here to that here, right? Yeah. Okay, and so.
Wait, no, that's closer to 400.
Something like that, right? But of course, there's a proper time axis here, and so that's why the index pulling out here is what MATLAB is going to give us. So time diff in this case is, you know, negative 350. That's our eyeballing 400. And did that, I did that. And so now I'll just plot that. And that's the behavior here. And so, yeah, it's oscillatory. It's not a pure sinusoid. In fact, it's a series of sinusoids. And by this analysis, you can figure out how to delay one versus the other. Okay. So now I'll do a new figure, or maybe I'll clear this figure. I'll do a new figure. And I'll do what we essentially did by hand, is to say, let me begin by eliminating time and just plotting S1 and S2 as a little cross plot, and I'll do that in subplot 221. S. Oh, come on. Oh, they don't have the same length, these signals. So never mind. I will do the first, what, 2,250. Let's try that. Okay, so you're like, axis equal is definitely what you want to do here if you're in the same units. If we're not in the same units, let's do this. Let's say S11, just for simplicity, is the first ones of those. S22, I just want to shorthand, is this. I'll make it bigger so you all can see it. And I'll go back and I'll redefine S11 as S11 minus the mean of S11. Oops. So centering and scaling, always a good idea. Divided by the standard deviation of that, forever now defined. Same thing for 2, 2. Replot my cloud here in this subplot. Okay, and then I'll say axis equal an image, but how about equal? Then at least I'm looking at the same numbers of standard deviation representing the same amount. And then I really better do it, make it pretty, and go axis, let's say -5 to 5, 5 to 5. Oops, not good. Also not good.
Sorry, for S22, like a few lines above, I think you subtracted the mean of S11.
Luckily, it doesn't matter much because these signals have the same means, more or less. But thank you for noticing. I'm going to fix that, right? There is that. There is this. And plot it again in the subplot. I'll begin with the query. I'll plot it. And I'm going to plot S22 versus S11. Now I'm going to say axis equal to make sure that if it's square, I have it square. And now I'm going to say my axis to -5 to 5, and I'll do my grid on. And let me ask a question of Snowstorm's turn. Why is -5 to 5? Like, just help me understand why that's almost always a good choice.
That includes like pretty much the entire distribution, like between -5 and 5 is that score.
So yeah, if the data were normal to begin with, and I've just subtracted their mean and I've just scaled them by their standard deviation, then they are still normal in a 0 to 1 sense, standard normal. And we know of the standard normal that, 5 standard deviations out, you've got it all. So maybe even overly generous here. So 4, 4, 4, 4, I'll still get it. But I like to show everything. Axis image would do it, but then it's going to be asymmetric because, who knows what you hit. And so be deliberate about your axis scaling, okay? And then label and so on. So now we'll do a subplot 2. And I'm going to say, I'm too lazy now to figure out which one was later. But I knew one of them was delayed by 350. I'll just do 2 cases, right? If I do 350 to the end, or let me just say, what is the length of S11? What is the length of S22? That's 2150. I've set them to be equal. So let me plot my second subplot. And let me go in beginning at 350 to 2000. And then let me begin at 1 and go to 2000 minus 350. Plus or minus 1, it'll complain if it's not good. 49, is that it? Okay. So here's the grid on. I'm still in my standard units. I'm still in my axis equal. And now you know for sure that if I cross-correlate that, if I ask, I have cross-correlated, I already know the answer, right? So now I'm going to ask for the correlation coefficient between this and that. And so it's this, right? It's 0.86. So this is 87% correlated if I do it like this. I told you I'm not looking carefully at the sign. I'll make a third subplot. And I'll plot the 1 to 2000 minus 349 here, and the 350, 2000 here. Now they're a little different symbol. I'll do it correctly. And that wasn't it, right? So if you miss the time lag, and look at the wrong thing, then you are clearly not doing it, right? Check the correlation coefficient. Well, I'm not going to do it. You see it's low, right? And so maybe a third case in between, because that's really what ultimately MATLAB is doing for you. You would do it like this if it didn't already exist. You'd say, well, I don't know, but let's say the correlation is, you know, it's 450 samples off. Who knows? Actually, let me do it like this. Let me go slightly below. Let me go back to the second plot. I'll make it the fourth plot. Let's say I'm off 375, 374. I then need to see that this is not a complete, you know, tight ellipse, right? And so every case is in between. If you did this iteratively for every lag and you computed a little correlation coefficient, you would come up pretty much with the thing on the bottom left of figure 1 here, namely the properly normalized correlation coefficient. Xcore does that for you, and so you can read that off. Note that I would never want to publish a plot like this because all the dots cover each other, and you might want to go to a hist 2D histogram like in the sketches that I flashed for you on the screen here, which is also already available in MATLAB. Much better to do a density plot, but you and I want to agree that if you look at my figure 2 in MATLAB now, that it's not very informative. If you make a plot like that and all your crosses cover each other, don't bother, right? We don't want to see that. We want to see you do more things. One of the things here is to say, aha, they're all misaligned. It's not a complete beautiful circle because there are all sorts of radii involved, right? So you have to see this circle that I began with. That's the situation for one sign and another sign at the same amplitude. This particular signal, this test signal, has multiple signs of different periods with different phase lag lead relationship and with different amplitudes. And so that's why it fills the whole disk with dots. So all what we've done before, correlations between variables, eliminating time variable, interpolation onto a common time axis so that you can eliminate the time variable, doing this business of cross correlation, doing these beginnings of Fourier analysis that we're still going to talk about, but that we've already done in terms of the period fit code that you have to figure out the contributions of the daily versus the seasonal cycles. That's all wrapped in here, right? Okay, I got 12 minutes and I have something to say in those minutes, unless you want to lead it somewhere else. I will talk about the significance. All good?